Alrighty, so we'll go ahead and go. The bell work says Maria plans to rent a boat. The boat rental costs $60 per hour. She will have to also pay for a water safety course that costs $10. Maria wants to spend no more than $280 for the rental and the course. If the boat rental is available only for a whole number of hours, what is the maximum number of hours for which Maria can rent the boat? So this one, it's all about picking out information. It's going to set up like a linear inequality. So with the key being $60 per hour, and then she has her $10 boat class, and we all want that to be less than or equal to $280. Okay, so that's the equation that we're dealing with. If we're able to solve for h, we're going to find the meeting point, or what h value would make 280. So we're going to solve for it. So we're minus 10 from both sides. Get 60h is less than or equal to 270. Divide by 60 on both sides. And we're showing that h is less than or equal to 4.5. But here, that's a decimal. So they only rent it in whole. Okay, we can't go to 5 because that would exceed our limit, $280. So we have to go back down to 4. So the most amount of hours that she could rent it is 4 hours and still save a little cash for her. So bang, here we go. Slideshow from the current slide. Okay, so we do have lecture today. It shouldn't be too terribly difficult. We're going to talk about rational functions. Okay, and a rational function is functions that are going to have infinite discontinuities. They're going to have horizontal asymptotes and vertical asymptotes. Okay, or places or lines that the graph approaches but never really touches. Okay, so limits is going to be a part of it. On asymptote, like I said, if you can imagine an infinite discontinuity, like the equation 1 over x, so the horizontal asymptote would be at the y or at the x-axis, and the vertical asymptote would be at the y-axis. Those, by any other definition, an asymptote is a line which your graph approaches but does not touch. So if we had this function with an infinite discontinuity right there, you would have a vertical asymptote right there, and you would have a horizontal asymptote that comes across between both of those. Sorry, that's not a very good graph, but your horizontal asymptote would look something like this. Okay, so we're going to be dealing with a lot of undefined functions. Okay, we're going to find those by factoring. So factoring is going to be a big part of this section again. But comparatively, it should be a pretty simple section, nothing too difficult. You have vertical asymptote, which limits the domain, that they only occur when you have an undefined. You have the horizontal asymptote, which limits the range, okay? Just a value that it will approach, but it will not reach. So where your graph kind of levels out. You have an oblique asymptote, which kind of looks, it's still an asymptote, meaning that you're going to approach it, but you will not meet it. But oblique means that it's just off camber, okay? So it's kind of like a diagonal asymptote. Holes, okay? Holes are removable discontinuities. Okay, so whenever we have a graph with a removable discontinuity, that's what's known as a hole. It's technically undefined, but it doesn't create an infinite discontinuity. Okay, so these are what some rational functions look like. Okay, you can see we're talking about vertical asymptotes on the left and horizontal asymptotes on the right. It says the line x equals c is a vertical asymptote of the graph of f if the limit as x approaches c from the left, f of x goes towards a positive or negative infinity, or the limit as x approaches c from the right, f of x is equal to a positive or negative infinity. So like I said, it's a line which it appears your graph is going to approach, but it skyrockets off to positive or negative infinity. Okay, so the closer and closer we get to it, the higher our values are in this case, because both of our limits are approaching positive infinity. Okay, so your infinite discontinuities. A horizontal asymptote of the graph of f is if the limit as x approaches negative infinity, f of x equals c, or the limit as x approaches positive infinity, f of x equals c. So you can see with a vertical asymptote, x is approaching a certain value of c, right? And then the closer we get to that, we go off to a positive and negative infinity. But for a horizontal asymptote, you're really talking about in behavior of the graph, because you're dealing with the limit as x approaches a negative infinity and the limit as x approaches a positive infinity. And the value of c will change. Okay, but all your rational functions, they're going to be presented to you in this type of form, where you'd have, so we'll say the rational function f of x is equal to the function of g of x divided by h of x. And h of x cannot equal 0. Okay, so this format is your rational function. So you can see that you're dividing. Okay, whenever h of x is equal to 0, you have a vertical asymptote. Okay, whenever this function equals 0, because that causes anything to be undefined, those are your vertical asymptotes, or a hole. But I'll show you how we can find that. Okay, your horizontal asymptotes have a ton more rules. Okay, but they center around the degree of the equations that you're working with. So here are your rules for finding horizontal asymptotes. So it says if f is the rational function given by f of x is equal to ax divided by bx, then it lists out the expanded polynomial. The key portions that you want to pay attention to are an, xn, so the leading coefficient, of ax, and the degree, and the leading coefficient of bx and the degree. Okay, where bx can equal 0, that's when you have your vertical asymptote. So whenever the denominator is a 0, that's a vertical asymptote. They have no common factors other than plus or minus 1, then the graph of f has the following characteristics. So having common factors between ax and bx. So we will enter into a situation where we factor out this top polynomial and we factor out this bottom polynomial. Okay, because those are going to help us, one, find the vertical asymptotes, because factoring the denominator and setting it equal to 0 is a quick, easy way to find zeros. And then we want to pay attention for any common factors between the two, because that's what causes holes. Okay, we have a hole when you have a common factor in ax that also appears in bx. So vertical asymptotes may occur at the real zeros of b of x. So whenever b of x is equal to 0, but we're paying attention to horizontal asymptotes. The graph has either one or no horizontal asymptotes is determined by comparing the degree of n of a of x to degree of m of b of x. So once again, those are the leading coefficients, okay, the highest exponents. And what it says, that if n is less than m, okay, you have a horizontal asymptote at the x-axis at y equals 0. So once again, that's if the degree of the numerator is higher than the degree of the denominator, you have a horizontal asymptote at y equals 0. Okay, pretty simple, pretty easy. If they are the same, talking about the degree, if n is equal to m, you have a horizontal asymptote at an over bm. Those are actually the coefficients, okay, or the numbers that are set out in front of your leading term. And then if n is greater than m, so the numerator's degree is higher than the denominator's degree, there are no horizontal asymptotes. Okay, the intercepts, the x-intercepts, if any, occur at the real zeros of a of x. The y-intercept, if it exists, is the value of f when x is equal to 0. Okay, or in other words, we're going to plug in 0 to find our y-intercept, the same way that we would with a quadratic, the same way that we would with a linear function. Okay, so we can find constants that way. But more or less, we're graphing two functions that have been divided by themselves. Okay, and I want you to pay special note to these. Those three rules underneath the horizontal asymptote, because finding the horizontal asymptote is probably one of the harder things to do. The vertical asymptotes are pretty simple because we can do that simply by factoring, but it's the horizontal asymptotes that definitely make the call. So I'll give you a couple minutes to jot that down. Any questions about that so far, or is that making sense to everybody? All righty. Let's work a couple problems. Okay. So finding vertical and horizontal asymptotes, we want to find the domain of f of x, which is equal to x over x minus 1, and the equations of the vertical and horizontal asymptotes, if any. Okay. So using our rules, okay, we know that there's going to be a vertical asymptote whenever our denominator function is equal to 0. So we want to think of a value that when we plug it in for x, what is going to cause that to be a 0? So if f of x is equal to x minus x divided by x minus 1, you can see whenever we plug in a 1, whenever x is equal to 1, this becomes undefined because it's a 0, right? 1 minus 1 is 0. So that means we have a vertical asymptote at x equals 1. Draw our graph here. So I have this dashed line where my graph will approach, but it will not meet it. That's because I become undefined here. Okay, but now looking at the horizontal asymptotes. Remember, we want to compare the degrees. So we have x to the first power and x to the first power. Those fall in where n and m are equal. So the horizontal asymptote falls where these coefficients are. Okay, we have a 1 and a 1 as the coefficients. So since our degrees are equal and our coefficients are just 1, we have a horizontal asymptote at y equals 1. Okay. So right there, I know where my vertical and my horizontal asymptote are just by knowing those two rules. Okay, and that's what they wanted us to find. They wanted us to find the vertical asymptote which is where our denominator function, whatever makes that equal to 0. Okay, so 1. And then our horizontal asymptote, since our degrees of the two functions are equal, it falls at where the coefficients, okay, if we just use the coefficients and divide them, we are fortunate enough to have 1 and 1. So we have a horizontal asymptote at 1. So finding the domain. Function is undefined at the real 0 of the denominator b of x is equal to x minus 1. The real 0 of b of x is 1. Therefore, the domain of f is all real numbers except for 1. Okay, and that's because that's where we become undefined. That is the only limit to the domain that we have. Okay, and you'll find that the domain of each of these functions is going to be all real numbers excluding your vertical asymptotes. Okay, I'll say that once again. The domain is going to be all real numbers excluding where your vertical asymptotes are. Okay, because those are the areas where your function becomes undefined. Okay, find the other asymptotes. So we already know, because we use the rules, that we should have a horizontal asymptote at y equals 1. Okay, this is them checking for the vertical asymptote. They build a table, and you can see that as we approach 1 from the left-hand side, we get farther and farther negative. As we approach 1 from the right-hand side, we get farther and farther positive. So our graph from that information is going to look something like this. Okay, with this branch coming here and this branch coming here. Okay, but once again, we have the vertical asymptote and the horizontal asymptote. So they're just using the table to kind of prove it. In this case, if we find the vertical and horizontal asymptotes, it'll be pretty simple to prove. So I don't really expect you guys to build a whole table. Okay, and there's their proof, confirming what we've already known. Then the horizontal asymptotes, like I said, we use the rules, so we know there's one at 1. So they use a table to identify and to prove that the rule is true. You can see the farther and farther you go to the left, our graph gets closer and closer to the value of 1. And the farther and farther we go to the right, our graph gets closer and closer to 1. Okay, this proves using limits that we have a horizontal asymptote at y equals 1. Okay, and then we could use Desmos to plug it in and check it to prove it. Like I said, it's a pretty simple section if you use the rules. Okay, the rules to find the horizontal asymptote, the rules to find the vertical asymptotes. Pretty simple, pretty easy. Okay, so here we have find the domain of f of x, which is equal to 4x squared plus 3 divided by 2x squared plus 1, and the equations of the vertical and horizontal asymptotes. X squared plus 3 over 2x squared plus 1. All right. What is that going to be? It's not perfect squares. All right. So we're working with this equation here. Finding the horizontal asymptote, this one's going to be pretty simple. We want to compare our degrees. Okay. And since they're equal, that means we have a horizontal asymptote at 4 divided by 2. And that comes straight from your rules. So we have a horizontal at 2. Okay, or at y equals 2. Because it's going to be that horizontal line. Okay, for the vertical asymptotes, this one's a little bit more tricky because we would have to factor this. Okay, we're looking for 2 terms. No greatest common factor to factor out. So I'm going to use my box here. Take 2x squared out. Put a plus 1. I'm going to multiply those together. So I'm looking for 2 terms that multiply to equal 2x squared that are going to add up to equal 0. Awesome. 2x squared plus 1. Looks like it's going to be a negative 1/2. What 2 terms are going to meet that? 2x squared. So this is prime. Or in other words, there are no real zeros for this equation. You can also, if you just think about looking at the graph, if we were to graph 2x squared plus 1 by itself, and I'll share my screen here again, because you're going to come across some that are that kind of stump you, the prime ones. So here's the graph of just 2x squared plus 1. Remembering that vertical asymptotes occur when this is equal to 0. But you can see our graph, if we were just graphing this one, is a parabola. It's above the y-axis or the x-axis, and it's opening upwards. So there are no real zeros for 2x squared plus 1. So it's a prime polynomial, so we can't factor it to find it. So in this case, since there is no situation where this equals 0, there are no vertical asymptotes. So the zeros of the denominator b of x are imaginary, so the domain of f is all real numbers. Or in other words, there are no vertical asymptotes. Okay, because the domain of all real numbers, the function has no vertical asymptotes. Using division, you can determine that. So that's them dividing. It's not really a mandatory thing. We're just concerned that this denominator equation never equals 0, because to give us the information that we need. So we found our horizontal asymptote by using the rules at 2. Okay, so we knew we had a horizontal asymptote at 2. We knew that because this denominator equation never equals 0, we don't have a vertical asymptote. So this would be the graph of the equation 4x squared plus 3 divided by 2x squared plus 1. Have a good one, buddy. Okay, here we got an easy one. Okay, it's easy because it's already factored in the bottom. So where are our vertical asymptotes going to fall? Well, the only number that makes the denominator 0 is 4. So x cannot equal 4. Okay, so that means we have a vertical asymptote at x equals 4. But now we want to look for our horizontal asymptotes. Once again, we want to use our rules. So we want to compare the degrees. This x is to the first degree, and this x is to the first degree. And since they are at the same degree, we have a horizontal asymptote at 5 over 1. And once again, that's just taking the coefficients of the leading term. Okay, we started with 5x plus 10, and we had over x minus 4. Since they're both to the first power, we take our two coefficients, this 5 and this 1, and we divide them to figure out where our horizontal asymptote is. So we have a horizontal asymptote at y equals 5. Okay, so the domain, we know x can equal 4 because that's where we have our vertical asymptote. And then we know we have our horizontal asymptote at 5, so we want to select an answer option that corresponds to both of those. So a couple of them that we can eliminate right off the bat is B, because it says x cannot equal 5. We know that x can equal 5, x can equal 4. Okay, looking at C, domain, x can equal 4, x is all real numbers, vertical asymptote at x equals 4, horizontal asymptote at y equals 5. So letter C is the one that fits all the requirements that we found by using our rules. So letter C is the correct answer. Okay. All right. So for k of x, which is equal to 7 divided by x plus 5, determine any vertical and horizontal asymptotes and intercepts, then graph the function and state its domain. Okay, so first looking at vertical asymptotes, what's the one number that can make our denominator 0? So the one number that does that is -5. So x can't equal -5. That's where we have a vertical asymptote. And that is the only limit to our domain. Okay, all other numbers that we plug in, we're going to be okay. So, but looking here to find our horizontal asymptote, we're going to use our rules again. Okay, what it says is that we want to compare the degrees. Okay, just to imagine if we had written it like this as x to the 0 power, so anything to the 0 power is going to be 1. So 7 times 1 is just going to be 7. I'm just doing this so that you can visualize it. This degree is less than this degree. So the degree of our numerator is less than the degree of our denominator. If it's just a constant, it's always associated with the variable x to the 0 power, because anything to the 0 power is equal to 1. Okay, but so we can use our test here. So this is where n is less than m. From our rules, that corresponds to a horizontal asymptote at y equals 0 or the x-axis. Okay, so now we can finish off and graph this. Get my thing so that I can write on my full paper. So we got our y-axis, we got our x-axis. We know that this is a horizontal asymptote. 2, 3, 4, 5. We know that this is our vertical asymptote. Okay, and a lot of our graphs are just going to be sketches. So we have a horizontal at the x-axis. We have a vertical at x equals -5. So in order to graph this really quickly and really easily, what I'm going to do is I'm going to plug in an x value on either side of my vertical asymptote. So I'm at -5. So I'm going to plug in a -4 and a -6. And I'm going to use just those given points to graph my equation because I know I have this horizontal asymptote and I know I have this vertical asymptote. So when I plug a -4 in, I get 7 divided by a +1 because -4 plus 5 is 1. So that's going to be 7. -4, 7. 3, 4, 5, 6, 7. That's this point. Okay, and then when I plug in -6, -6 plus 5 is a -1. 7 divided by -1 is a -7. 2, 3, 4, 5, 6, 7. So that's this point. Believe it or not, from this, I have enough information to graph it. Okay, I know my graph has these asymptotes. So I know it has to look something like this. And you can estimate that, or you could have plugged it into Desmos to find the same information. Just remember that we're going to approach our asymptotes, but we are never going to reach our asymptotes. Okay, and plugging in 2 points close to your vertical asymptote really kind of separates where they actually fall. So that's what our graph is going to look like. Let's take a look at how the book does it. Okay, so the function is undefined when b of x is equal to 0. Therefore, x can't equal a -5. That's where our vertical asymptote is. So because the degree of the numerator is less than the degree of the denominator, that means we have a horizontal asymptote at the x-axis. Okay, so they plug in even more points. Once again, we can do that just effectively with just plugging in 2, right? Because our graphs are basic estimations, and the key point is we got to be able to find the vertical and horizontal asymptotes. And right there is what our graph would look like. Okay. Here we have our next one. This one, okay, it says 4f of x, which is equal to x plus 1. So x plus 1. Why am I struggling with this today so much? Let's bring that down here. Somebody moved my document camera and they moved it out of my preferred area. So, love living with little kids. So f of x is equal to x plus 1 divided by x squared minus 4. Determine any vertical and horizontal asymptotes and intercepts, then graph the function and state its domain. Okay, so vertical asymptotes. What are the 2 x values that make our denominator 0? Okay, this here is a difference of squares. We can actually factor this out. Okay, and it'll be equivalent to x plus 1 divided by x plus 2, x minus 2. Okay, that's the factored form of that. It's difference of squares. Okay, so what that means is that we have a 0 at -2 and +2. So we have vertical asymptote at 2 and -2. Okay, so now let's look at horizontal asymptotes. Okay, horizontal asymptotes, once again, can determine based upon the degree. So here we have n, which is less than m. So we have a horizontal asymptote. Since n is less than m at the x-axis. Right there. Okay. But if you're thinking about intercepts, this is our horizontal. Okay, so thinking about our intercepts. Remember, our y-intercept is going to happen when we divide or when we can get f of x set equal to 0. So what we would do is we would plug a 0 in for f of x, and then we would solve that. So 0 is equal to x plus 1 by x squared minus 4. In order to get this out of the denominator, okay, we would have to multiply both sides by x squared minus 4. That's going to cause this side to cancel out. X squared minus 4. Okay. So anything times 0 is going to be 0. So once we carry out our multiplication, we have 0 is equal to x plus 1. We subtract 1. We get when x is at negative 1. So we have a y-intercept at x equals negative 1. What? Oh, that's x-intercept. X-intercept. Sorry about that. No. Negative 1 there. Right there. Yeah, it's a y-intercept. What am I doing? Because our horizontal asymptote is at the x-axis, so we can't have an x-intercept. We can only have a y-intercept. But from this information, we have enough to graph it. It's going to look something like that. It's going to look something like that. It's going to look something like that. Okay, that's because I have my horizontal asymptote at the x-axis, so I know my graphs can't touch that. Okay, my y-intercept being at negative 1. Right there. So again, this is showing where our vertical asymptotes are. So we know we have one at x equals 2 and x equals negative 2. Compare the degrees because there is a horizontal asymptote at y equals 0, so we have no x-intercepts. Numerator has a 0 at x equals negative 1, so the x-intercept is negative 1. So y-intercept is negative 0.25. Hang on a second. Where did I do my math wrong then? Degrees. Numerator has a 0 at x equals negative 1. How do they get? Oh, duh. Duh. I made a simple math mistake. So the horizontal asymptote, remember those are for end behavior. Okay, end behavior here. So when I solved it and I found the negative 1, that really was my x-intercept instead of my y-intercept. just a simple little math mistake because I set f of x equal to 0 and then I solved it that way to get -1. So that's where I hit 0. And then to find your y-intercept, you would plug 0 in for the equation, which would give you 0 plus 1, which is 1, and then 0 minus 4, which is -4, so a -1/4. That was stupid, Mr. Burns. That was stupid of you. Very, very dumb. Felt confident doing it though. Oh, I hate mental mistakes. God, no driving us. Okay, so we had a vertical asymptote at x equals 2 and x equals -2. Horizontal asymptote from the rule gave us 0. The x-intercept, we solved it correctly. We just labeled it as the wrong thing. And then for the y-intercept, remember that we always want to plug in 0 for our x. Can't believe I made that mistake. And then, like I was saying, the domain is always all real numbers, excluding where your vertical asymptotes are. Just dumb. I'm better than that. I'm better than that. Dang it. I'm better than that. Okay. So here, determine any vertical, horizontal asymptotes and intercepts. Okay. So horizontal asymptotes. On this one, remember that we have a constant in the numerator. So that corresponds to an x to the power of 0. So since our degree of our numerator is less than the degree of our denominator, we have a horizontal asymptote at the x-axis. Okay, to find your vertical asymptotes, what we need to do, because our equation is m of x is equal to 1 over x squared plus x minus 12. Okay, to find the vertical asymptotes pretty easily, we want to factor the denominator. So we're looking for two terms that multiply to equal a -12 that add to equal a +1. So that would be 1 over x plus 4, x minus 3. Okay, x squared, -3x, +4x, -12. Okay, so that means that we have a vertical asymptote at x equals -4 and a +3. So those are our limits to our domain. So x can't equal a -4 or 3 because those are our vertical asymptotes. And once again, that's just using the zero product property, trying to figure out where this gets to 0. So if we set them equal to 0 and solve, we'd get -4 and 3. So those are our vertical asymptotes and our horizontal asymptotes. So x-intercept. Okay, x-intercepts can only occur when the numerator is equal to 0. So since we have a constant in the numerator, there is no x-intercept. Okay, and then our y-intercept. This is where I made a mistake last time. So since our equation started out as m of x is equal to 1 over x squared plus x minus 12, we want to find what m of 0 would be. So that's 1 over 0 squared plus 0 minus 12. Okay, 0 squared is going to be 0, plus 0 is still going to be 0, so that's -12. Or our y-intercept is at a negative 1/12. Because that's what we get when we plug in 0. Okay, so now we want to choose an answer selection that solves it. They don't keep it in fractional form here for us. But looking at option A, vertical asymptotes at -4 and 3, that checks out. Horizontal asymptote at y equals 0, that's perfect. And then y-intercept at a negative 0.0833. If you plug into your calculator 1 divided by 12, you'll get 0.0833. So answer A looks good right now. Let's go through some of the other answers to figure it out. Vertical asymptotes, -4, 3 for B. Okay. B can't be it because it says the intercept's at 0. C, vertical asymptotes at 4 and 3. C can't be it because Pat doesn't get that one. And then answer D, vertical asymptotes in 4, -3. Horizontal asymptote at y equals 1. So all the other ones have false information except for A, leaving A to be our answer. Okay, this one, a little bit more involved, a little bit trickier, but if we stick to our rules, we're going to be okay, right? First thing, we'll write our equation. So f of x is equal to x squared minus x minus 12. And then I have 2x squared minus 8. Okay, so in this case, neither of these are prime, so I'm going to look to factor them. Okay, factoring out the top. I'm looking for two terms that multiply to equal a -12 that add up to equal a -4. It's going to be x plus 3, x minus 4 on the top. And once again, that's just the factors. Okay, looking at the bottom, we have 2x squared minus 8. We can factor out a greatest common factor here of 2. So that leaves us with x squared minus 4. So that's a difference of squares. So my bottom is 2x plus 2, x minus 2, like so. Okay, it's always beneficial to factor them out because you can learn a lot of information here. Okay, first being where your vertical asymptotes are. So we know that our vertical asymptotes are where this is equal to 0. So that means we have one at -2 and a +2. Tick, 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 tick. Okay. So those are our vertical asymptotes coming straight from our denominator. Let's look at horizontal asymptotes. So our equation started out x squared divided by 2x squared. Those are equal degrees. So we should have a horizontal asymptote. This is 1 at 0.5. Because 1 divided by 2 equals 0.5. Once again, just pulling the coefficients. So horizontal asymptote at 1/2, right there. Okay, the next beneficial thing is let's think about x-intercepts. Okay, x-intercepts. X-intercepts can only occur when our numerator is equal to 0. Okay, when these equal 0, because they don't have common factors, so we don't have any 4s or any holes, that means we have an x-intercept at a -3 and a +4. Once again, using the zero product property. there. That's there. Okay, so now our y-intercept. Okay, once again, that requires you to plug in 0. So finding the y-intercept, I'm going to plug 0 into our equation. So f of 0 is equal to 0 squared minus 0 minus 12 on the top plus 2 times 0 squared minus 8. Okay, so that's 0 minus 12. That's going to be a negative 12. 0 squared is 0 times 2 is 0 over a negative 8. So that is equal to a positive 3/2, which one falls right about there. So our y-intercept is at 3/2. Once again, you find your y-intercept by actually plugging in 0. My x-intercepts came from wherever my numerator is equal to 0. My horizontal asymptote came from checking the degrees and then pulling the coefficients. 1 divided by 2 is equal to 1/2. And then my vertical asymptotes occurred whenever my denominator was equal to 0, which is at -2 and 2. So from the information, we have x-intercepts, we have y-intercept, we have our asymptotes. So we can carry on and graph something that looks, helps if you hit your dot, something that looks like that. That's what our graph is going to look like. Okay, factoring both the numerator and denominator yields this. X plus 3 times x minus 4 with no common factors. Once again, the common factors cause holes, okay, removable discontinuities, and you'll see one. Okay, the function is undefined at -2 and 2, so our domain is all real numbers excluding our vertical asymptotes, which occurred at -2 and 2. The horizontal asymptote is at y equals 1/2. Once again, that was taking the ratio of the leading coefficients of the numerator and denominator because the degrees of the polynomials were equal. So we had equal degrees, so we just pulled the coefficients of our leading terms. The x-intercepts are at -3 and 4. That's where the numerator was equal to 0. And then our y-intercept is at 1.5 because when we plugged in 0, we got 3 divided by 2. And from all that information, we can graph it. See if we can find one with holes. That's not it. Okay. Oblique asymptotes. Last little note. Okay, once again, this is going to come from the degrees. So if f is the rational function given by f of x is equal to a of x divided by b of x, where b of x has a degree greater than 0 and a of x have no and b of x have no common factors other than 1, then the graph of f has an oblique asymptote if n is equal to m plus 1. So that's the degree of your numerator is exactly 1 greater than the degree of the denominator. Okay, so they have the equation. X squared divided by x plus 1. You can see our degree of our numerator is 2. The degree of our denominator is 1. Okay, and then the function for the oblique asymptote is the quotient polynomial q of x resulting from the division of a of x by b of x. So oblique asymptotes, we have to divide. All right. Let's get one that has it. Okay. Determining the asymptotes and intercepts for f of x, then graph the function and state its domain. So let me write it down. So we have f of x is equal to x squared plus x minus 8 and x plus 3. Okay, so vertical asymptote. What causes our denominator to be 0? Since it's x plus 3, that means at negative 3, we have a vertical asymptote. So that is what would cause that. Okay, horizontal asymptotes. So n is greater than m. So 2 is greater than 1. So that does not, if you go back to your rules on horizontal asymptotes, it says that there shouldn't be a horizontal asymptote. But this fits n is equal to m plus 1. So the degree of our denominator is exactly 1 less. Okay, so that means we have an oblique asymptote. Okay, how do we find the oblique asymptote? We do division of polynomials. Okay, x, what do I need to multiply x by to get x squared? That's going to be x, so x times x squared is x squared. X times a positive 3 is a positive 3x. Okay, do my subtraction. I get a 0. Get negative 2x. Drop this down at negative 8. So x minus 2 gives me negative 2x. That gives me negative 6, 0, negative 14. Okay, the key thing. Since we had it fit the form for an oblique asymptote, because the degree of the numerator was exactly 1 larger than the degree of the denominator. Okay, when I do my long division, I don't care about the remainder. Okay, I care about this x minus 2. This is the function for our oblique asymptote. So if I were to draw my graph here, and I'll just get it started, I know I have a vertical asymptote at negative 3 here. Because it fit the form of my oblique asymptote, 2 positive there. This is the line x minus 2. This is my oblique asymptote. Okay, it's oblique because it's not a true horizontal. It's on where it has a slope. Okay, and this is the equation of my oblique asymptote. So this is the line x minus 2. Here. Okay, talking about intercepts. Okay, to find your x-intercepts, the easiest thing to do is to make sure that we're in the factored simplest form. X squared plus x minus 8. So looking for two terms that multiply to equal a negative 8, but add up to equal a positive, I don't think that's factorable. 3 and 4. Okay. Let's do my box. See if that helps. X squared negative 8. They multiply to equal negative 8x squared, and they add up to equal a positive 1. 1 and 8, 2 and 4. Yeah, I think that's prime. So there are no x-intercepts. Well, there has to be. Multiply to equal negative 8, but add up to equal positive 1. No, no. What am I missing? It's not factorable. It's prime. Okay, I'm going to say this doesn't have an x-intercept because I can't think of two terms that would equal that. Weird. Okay. So y-intercept. Once again, that comes from plugging 0 into our equation. So f of 0 is equal to 0 squared plus 0 minus 8 over 0 plus 3, which is equal to a negative 8/3, or 2 1/3. So 2 1/3 is right there, like so. Huh. Weird. Why would they give you a prime one? And then we would use that information to graph it. So that's the domain and the vertical asymptote. It's everything except for negative 3. The degree of the numerator is greater than the degree of the denominator, so there is no horizontal asymptote. There's that oblique asymptote. Okay, polynomial division. So they divide it out, and they get x minus 2 with a remainder. So once again, we don't really care about the remainder. This x minus 2 is the function or the equation for our oblique asymptote. Therefore, the equation has an oblique asymptote at y equals x minus 2. Okay. That's just rude. Okay, the x-intercepts. Once again, they occur where the numerator is set equal to 0. This one they did using the quadratic formula. I was trying to factor it because it was prime. So the y-intercept is about negative 2.67 because f of 0 is equal to 8 divided by negative 3. Graph the asymptotes, and that is what our graph looks like. You can see with the oblique asymptote here. Alrighty, so we got about 20 minutes left. Are there any questions right now at this time? This one was kind of a fun one because this hit prime. So in the event, if you have a prime equation like this, just remember what you have in your toolbox, which you could use. You could use the quadratic function, the quadratic formula to find the zeros, which is x is equal to the opposite of b plus or minus b squared minus 4ac all over 2a. And they would just plug this polynomial in with a, b, and c. They could plug it in there. Or you could graph it. And this is in the event that it's prime. If it's not prime, that means it's factorable. It's pretty simple. It's pretty easy. But if I were to graph this, plus x minus 8. Okay, and you can do this on a graphing calculator or Desmos. So here's my numerator function. And the reason that we're concerned about this is because our x-intercepts occur where this is negative. So, or where this is equal to 0, or the x-intercept of our top equation is where our x-intercepts occur. So we have a 0 here at negative 3.372 and a 0 here at 2.372. If I go back to this, to our graph, you can see our zeros, or our x-intercepts, match to where our zeros are here. It's roughly about 2.72, and that's a negative 3.3. Okay, but that's probably that was just a very difficult question, but that's in the event that those are prime. You can use the quadratic formula and find the zeros that way, or you can graph it, but the first option is to factor it. Okay.